He might be a minute or two delayed, but we are expecting him to give an intro for our speaker today. So, my name is Emily Jessling with Quasi, and I, before we get started, also want to remind you that we are having presentations on this theme every Friday at 3 p.m. Eastern throughout October. The next speaker is Bridget Scanlon from the Bureau of Economic Geology at the University of Texas, Austin. And our full speaker list is on our website, along with titles and abstracts as they are updated. As a heads up, I will be muting everyone. If you have any questions during the presentation, please write them into the chat box. We will also have a Q&A period at the end of the presentation where you can also write in your questions into the chat box, and we'll try to address them in the order at which they were received, more or less. And while I have a minute here, I also want to remind everyone that the Quasi Pathfinder Fellowship application period is open until October 16th. If you have any grad students who would like to take their research or their research ideas and go to another location, learn or apply a new technique, we have the application open for that. It's also linked on our website. And if you'd like, actually, I will put the direct link into the chat box. But this is an opportunity to get up to $5,000 in travel reimbursement. So if there are any graduate students out there who want to do kind of an extended field work or exchange opportunity, this is ideal. Okay. Oh yes, now we're at 3:05, so I think that Todd Caldwell had warned us that he might be a little delayed, so I think we can get started. And Steve, if you would be so kind as to give yourself an introduction, and that we can get a move on.
Excellent. Thank you very much. So good afternoon. My name is Stephen Quiring, and I'm an associate professor in the Department of Geography at Texas A&M University. I've been at Texas A&M since 2005, and my research focuses on drought monitoring, drought prediction, land-atmosphere interactions. And so I'm grateful for this opportunity today to share a few of the exciting things that are going on in this area. And I'm certainly representing a large group of people who I will mention here as we go through. So there, in terms of the projects that I'm involved in right now, the ones that I'm going to focus on today are first the Coordinated National Soil Moisture Network, and this is a NIDIS funded initiative that is about 1 year into its life cycle. So we started work on this in September 2014, and there's a pilot soil moisture portal that's stood up that I'm going to spend a little bit of time talking about, and this is sort of one of our first opportunities to publicize this and to begin to spread the word. And so I look forward to getting input, feedback, suggestions on it, and especially as we're just starting the second year, the second phase of this pilot, looking forward to identifying other partners and use cases and really enhancing the value of this information. The second thing that I want to talk about is more on the land-atmosphere interactions and seasonal climate prediction or climate forecasting, and this is part of a 5-year project that is in its final year, funded by the National Science Foundation. And so for this particular project, we're really interested to identify the role that land-atmosphere interactions play in either initiating or exacerbating drought conditions. And the work that I'll present today is just one component of that, looking at the relationship between soil moisture and monthly to seasonal predictions of extreme temperatures. And then the final thing is an advertisement for something that is extremely new, and that is the Texas Water Observatory, a project funded internally right now at A&M by the Vice President for Research to establish a set of critical zone observing sites in the Brazos watershed here in Texas. And the purpose of advertising that is first of all that we hope that this is something that can grow to be a Texas-wide observing network and link to existing stations and networks and observations that exist, but also that we're seeking partners and input and suggestions as we go through the experimental design phase this fall, and with the goal of putting sensors in the ground next year and having the network in observation or in operation next summer. And there are some other related activities that I don't have time to talk about today, but just to sort of put those up there to say that this is a couple of the activities that fit into a broader research program. So first, to start out with, the Pilot Soil Moisture Network website is available here, ceta.usgs.gov/National Soil Moisture Network _pilot. I encourage you to check that out. And like I said, you may or may not have heard about this because it is, we're just in the phase of beginning to publicize and roll out the information on this. This is a collaborative effort. There's a lot of different federal agencies that are supporting and involved in this effort. The funding for the pilot project came through NIDIS, but there's heavy involvement with the USDA, NRCS, USGS, and my colleague Jessica Lucido at USGS CETA has been instrumental in leading and putting this together. And so what is the purpose of the National Soil Moisture Network? Well, this fits into and came about through one component of President Obama's Climate Action Plan, this idea that it is development of a national drought resilience partnership, and that soil moisture and soil moisture observing and this National Soil Moisture Network is a key component of that. And as it currently exists, there's a lack of coordination in terms of data collection standards when it comes to soil moisture. There's a lack of coordination in terms of data availability. And so when it comes to either drought monitoring on a real-time basis or more retrospective analyses, it's extremely challenging to pull together the various observed data sets that exist, because it requires going to 10, 20, 30 different places, navigating the various methods that they have for accessing the data, and then coming up with ways to standardize and integrate data that's collected using different sensors at different depths. And so this is also seen, and part of the motivation behind this is seen as, when we think of the global hydrologic cycle and or the water balance, this is one of the critical pieces of the water balance that is relatively underrepresented in measurements and in observations, and certainly is something that is extremely important, as I'll come to talk about in the latter half of my talk, in regards to thinking about land-atmosphere interactions and drought predictability. And so the current landscape of soil moisture looks something like this, and certainly this does not reflect all of the various sources of information that are available, but it gives you some flavor for the various types of data that currently exist. So NRCS runs the Soil Climate Analysis Network, and that's shown as one of the screenshots right here. There is the U.S. Climate Reference Network. Both of these are in situ measurements at various depths in numerous states, and the scan stations, some of them have been around for quite a long period of time. The CRN stations are relatively short in their period of record. These data are available in real time, and so there are various ways, FTP sites and web services, that one can access them through. There are also historical data collected at these points. The second way that data has been collected and integrated, and this is kind of reflects my involvement in the project, is through the North American Soil Moisture Database. So soilmoisture.tamu.edu. This is the project that was funded through the National Science Foundation to develop a retrospective national, well, actually continental scale, although the vast majority of observations are within the U.S. and relatively fewer in Canada and Mexico. But the idea of developing a comprehensive, integrated soil moisture database for supporting scientific analyses of land-atmosphere interactions and for validation and calibration of satellites and models. And so, again, it's primarily a historical database. At present, we don't have a way to update the data in real time, and it's not meant for visualizing or depicting current conditions in terms of moisture across the United States. And so because of that, these different options, it opens up the potential, the need, it demonstrates the need for something that focuses more on real-time and supporting use cases that require integration of data from multiple sources. The third sort of leg of the stool is model-derived and satellite-derived data sets, and obviously there are many different agencies involved in the collection of soil moisture data, either through remote sensing or through running hydrologic or land surface models. And so those have national or global coverage and provide very useful sources of information. But again, they tend not to be integrated and available with observations on kind of the same timescales and same grid. And so one of our motivations as we continue to build this out is to integrate all three of these into a single readily accessible, publicly available site that people can access and visualize data. So for the initial phase of our project, we focused on some use cases, and these use cases were to help us identify who the users are and what their needs are, and therefore to identify what are the essential characteristics that this national soil moisture network should have. And so the first use case, and the one that I'll kind of focus on today, is this idea of operational drought monitoring. So providing this national soil moisture network in support of the U.S. Drought Monitor and the weekly updates of that. A second use case, and what is in terms of experimental land surface modeling and the need for observations to help set the appropriate initial conditions. And then the third is operational hydrological modeling. So we had conversations with hydrologists from the river forecast centers and discussions that for many of the models and output that they're using, they do not have a good indication of what initial conditions are, and so observed soil moisture data would be helpful in constraining their forecasts, their operational flash flood forecasting. And so the common denominator here is this need for real-time nationwide soil moisture data in an accessible format, and that not only to visualize the data, but to make the underlying measurements themselves available through a web service, and also to visualize them. And so that's what we set out to do with the pilot over the last year. And so we developed a number of storylines, and Jessica Lucido was instrumental in this in terms of helping to focus us on what the key aspects are that needed to be part of this web portal. And so here's just an example of what those storylines look like that support these use cases. And so this one says, as a drought monitor author, I want to see a map of percentiles of current volumetric water content at discrete common depths related to a long-term record, color-coded using the U.S. Drought Monitor legend, so that I can determine how to make necessary changes to this week's Drought Monitor map. And so that's one of the things that we set out to do. And as you'll come to see in a few moments, not all of these things are 100% achieved at this point, but we've certainly made progress over the last year. So with the pilot, we certainly didn't try to address all of the networks, all of the data sets, and we focused geographically, and we focused in terms of the networks that we were working with. And so the pilot focuses on integrating data from the Climate Reference Network, the Soil Climate Analysis and SNOTEL networks, Oklahoma Mesonet, and West Texas Mesonet, and geographically focuses on the Texas, Oklahoma, Arkansas region that's depicted in the map. In addition, we propose as part of the pilot to integrate data from the North American Land Data Assimilation version 2, so that we would have model-derived data from NOAA, Mosaic, Sacramento, and VIC as additional data layers that are served through this web portal. And that is something that is yet to be finalized. So when we look at how the system is designed, this kind of gives an overview of our system architecture. And so there are a number of key components here. The idea that we collect and serve both metadata and the soil volumetric water content itself through web services, that we consume, so web services that from the Climate Reference Network scan Oklahoma and West Texas, and then there is a mediator aggregator that resides at the USGS CETA that consumes those services and then provides the data through the web portal in a common format. And so the kinds of things that need to be done in terms of aggregation include calculation of percentiles. So this is one of the ways that we're serving the data and providing it other than just the raw volumetric water content, and the choice of percentiles was informed by the need to support U.S. drought monitor kinds of activities and the fact that it allows us to use the historical observations at a site to give an indication of the relative water content in relation to what's normal for that location and for that time of year. And so this helps us when we're producing a national map so that we don't just produce a map that shows us what soil texture is, so that we would expect higher volumetric water contents in clay soils versus more sandy soils, and that wouldn't be particularly useful for thinking about the relative moisture conditions compared to what normally is expected at that site. And then finally, there are some map-based visualization tools and this USGS database also serves out a web service that can be consumed, so that in addition to the website that we've produced, if users would like to integrate these data within their existing websites or products that they're producing, they can directly consume the web service from USGS. This shows an example from yesterday of what the map looks like at present. So this, because the data from these different networks is measured at different depths, one of the things that we had to decide was how we were going to handle those differences in depths. And so at this point, we are binning the data. So this represents all of the stations that have a in situ sensor in the top 10 centimeters of the soil. Some of them may have a sensor at 5 centimeters. Some of them may have a sensor at 2 centimeters. Some of them may have a sensor at 10 centimeters. And so that is certainly one of the things that could be addressed. Certainly one of the things. And so the other thing that's depicted here is our way of visualizing the data. So rather than showing volumetric water content, this shows the percentile. So for each location, it is based on the historical CDF for that location. And so for October 1st, this compares historical conditions for the period of record at each of these sites to give us a relative ranking of wetness or dryness. So the work that's been completed to date on this, metadata has been gathered for all of those stations, which includes the type of sensor, the depths, information on soil characteristics at each of the depths where the sensors are available, the land use, land cover, and other ancillary information about the station and the site. For the purposes of the pilot, because most networks that provide soil moisture do not have their own web services established, we have established web services for the West Texas, Oklahoma Mesonet, and Climate Reference Network, and then we're directly using the SCAN web service that exists. This is fine for the purposes of a pilot, but obviously as we're thinking about scaling this up to and beyond the pilot to the National Soil Moisture Network, it's one of the issues that we have to address, because at present we're not planning to host or collect the data for these networks. We're just aggregating them and integrating them and providing them in a single, relatively, hopefully usable format. And so the other things that we've done, the mediator's been coded to access these data to calculate the percentiles. We have interactive maps, and then we have some relatively basic quality control that's been done for these sites. And then we have an outward-facing SOS service that aggregates the data from each of these 4 networks and provides it to whatever other users and websites and portals and applications that people would be interested in using this data. So I think that's one of the key things, is we're not expecting that the existing website is the be-all and end-all from the National Soil Moisture Network, that perhaps even more important than having the existing website and our methods of visualizing it is to provide the data so that other users, whether it's U.S. Drought Monitor authors, river forecast centers, researchers, or those involved in state and federal management can utilize the data in a way that makes sense for them, and they don't have to navigate the process of figuring out. Right now we have 4 networks aggregated. Hopefully, as we scale this up, we will increase to include 20, 30, 40 or more networks from across the United States, and so that will alleviate the need for each person to figure out the data format for those, how to get the data in near real time, and how to integrate data that's collected in different ways. So one of the sort of science-related components of this was figuring out how best to represent volumetric water content from disparate sites. And so this is related to the issues of variations in soil characteristics and the difficulty in coming up with a national map that in a useful way depicts conditions. And so we've, through our investigations, settled on percentiles as at least one relatively useful way to standardize the data. And so one of the challenges is, of course, many of these stations are relatively short-lived. And so their period of record, they may have only been established for 3, 4, 5, or 8 years. And as a climatologist, obviously we would think of this as being typically insufficient to calculate stable percentiles. And so we investigated how much the period of record influences this, and to try and establish a threshold to say how many years of data do we need from a station before we can establish relatively stable percentiles. And so the results that are shown on this particular slide are based on a bootstrapped reanalysis of the observation. So here we synthetically generate, the entire period of record is 15 years for this station, and then we synthetically generate multiple realizations of the period of record by resampling with replacement from those 15 years. And then we calculate the cumulative distribution function for each time that we do this, and then plot them here just to visualize them on the same. So each one of these graphs represents one realization where we've generated a record of 3 years, 6 years, 9 years, 12 years, and then the entire 15-year record from the original data, and then plotted the CDFs on top of each other to represent that. And so what is sort of shown here, but could be better quantified, is that in our analysis, based on the stations that we used, as long as we have at least 3 years of data in most locations, we can get relatively stable percentiles, and that the errors are relatively small. Of course, there are situations where this doesn't show up as well, and so if we look at this particular graph here, we see that there's a lot more spread between the CDFs. But in general, we found that this method's relatively robust. So what did we learn from going through this pilot project over the last year? And the first thing is that it's fairly uncommon for soil moisture data to be served via web services. And so our initial hope was that we could just utilize and consume existing services such as the one that exists for the NRCS Soil Climate Analysis Network, and that which we believed existed for the Climate Reference Network. But it turns out that one of the challenges in building this National Soil Moisture Network is the need to create web services for most of the networks that we'd like to include in terms of data. The ones that do exist often don't have a lot of documentation, which is a limitation, and one of the things that we hope to address with the National Soil Moisture Network is that we not only want to have this SOS service that we can provide, but also to provide adequate documentation so that any user can relatively easily consume these services and use them for their own purposes. In addition, station metadata were not available from any of the networks via a web service, and so that's, again, something that we established for the National Soil Moisture Network and something that we see as extremely important, so that not only serving out the data as a service, but the metadata so that people can make their own decisions in terms of quality control, or if they're interested in only looking at data collected with a particular type of TDR sensor or at a particular depth or in a particular soil type, that they could sort and subset the data as needed using information from each of those stations. A additional lesson learned was about how dynamic these networks are. So any solution that is created needs to be flexible to account for the fact that stations come on and offline all the time, and that we want to be able to include, for the purposes of showing near real-time soil moisture conditions, all of the available data that we can get our hands on. And so we need to have a solution that is flexible in that regard. And then finally, something that we're working on writing up the results for so that we can kind of use this as the justification and basis for using this percentile approach, is demonstrating that even with relatively short periods of record, the percentiles are quite stable at most of the sites that we've been working with, and therefore this is a reasonable approach. It may not be the only useful approach that one could take when it comes to visualizing or representing these data, but it, again, because the underlying volumetric water content is being served as a service, if there were other ways that people were interested in using these data, that they would have the flexibility to do that. So there are some things that are going to happen that need to happen yet, and that's also one of the places where I hope to encourage people to provide feedback, is that as you begin to look at this website, the second bullet here talks about modifications and improvement based on feedback. And so the color scheme that we're currently using doesn't correspond exactly to the U.S. Drought Monitor color scheme, which is something that was an initial goal. It's relatively thin right now in terms of the documentation and amount of technical support that's provided on the website, and so that's something we are continuing to work on. And then finalizing the documentation and frequently asked questions and those kinds of things are things that we'll be rolling out here over the fall. And we will be presenting this, so this is, I guess, the first truly public presentation of what we have for the National Soil Moisture Network at present, but there will also be presentations at the American Geophysical Union meeting and AMS coming up. So this is the year one of the National Soil Moisture pilot, and there are obviously many additional things that need to be done to increase and build on what exists to date. And so I've highlighted a few of those things here, starting with building out the system infrastructure. What exists works, but it's not built in a way that is sustainable in terms of, for example, adding in historical data. So what's available right now is the near real time. So when you go to the site, you can get the current hours soil moisture conditions across the United States. But if you wanted to look at what it was a month ago or a year ago, we don't have that, as we're not caching the data. And so that's a potential place to really enhance the value of this by archiving and allowing for utilizing of the historical data. A new or an additional thing that we wanted to do, which was included in our scope of work initially, was integrating NLDAS and SMAP data, and so that remains a high priority item that we'll be working on over the next year. And then surveying federal, state, and local agencies to identify other soil moisture data sources. There's approximately 40 networks that are included in the North American soil moisture database, and we hope to include many of those ultimately in the National Soil Moisture Network. But we know that there are many other sources of data that exist out there, and we're interested in, first of all, making agencies aware of this effort and inviting them to contribute data and share data as part of it, and then also to identify new use cases so that we can really make this maximize the utility for the greatest number of different users. And there are a number of other things that are listed in here as well that are important, laudable goals, but I'll let you sort of read those. So I think what I'd like to do, because I'm going to shift gears after this slide to kind of the land-atmosphere interactions, drought prediction stuff, is to pause so I can catch my breath. And if people have questions that they want to share at this point, please type them in, and I will happily do my best to respond to them, or to at least make you aware of who the people are who can better answer them. All right, so good question from Krista. Did you work with the Goddard Space Flight Center, DAC, to enable the web services for NLDAS? For both SMAP and NLDAS, we've had conversations with a variety of people. So I've been working directly with Yulong Shah at NOAA EMC related to the NLDAS data, and for the SMAP data, Vanessa Escobar and a number of others at NASA have been kind of our contacts for that. All right, I will wait and see if anyone else is going to type a question for a minute, and then we'll go from there. All right, yes, thank you, Krista. I will definitely follow up. All right, Andrew asked a question about knowing more about particular soil moisture sensors. Great question. We have certainly done some comparisons in this particular project to attempt to integrate and standardize across different networks. Probably an even better place where this has been done is the Morena, Oklahoma intersensor or sensor intercomparison testbed that Mike Kosh and Tyson Auctioner are involved in. So we can definitely chat about this, but I think since it involves talking about specific sensor manufacturers and such, it's probably better for an offline conversation. All right, and Pierre asks about data quality and responses of sensors. So there are definite, at this point, we do quality control of the data, but these quality controls are relatively, because it's based on real-time data, they are not as robust as the things that are implemented, for example, on the North American Soil Moisture Database or the International Soil Moisture Network. And so this is one of the factors that I guess relates to this idea of building out system architecture or infrastructure, and the idea that we want to develop a rolling cache, a historical set of observations that are archived at CETA so we can use some of those observations to better quality control the data in near real time. And this also, I think, highlights the differences between the National Soil Moisture Network, which is meant to be a near real time source for data versus some of the retrospective data sources or archives like the North American Soil Moisture Database or International Soil Moisture Network, which are meant to support satellite and land surface model, CalVal, as well as other scientific applications. And so there definitely are significant variations in quality. Our sort of an overview statement that I can make is that we actually see that when sensors are calibrated and maintained, they do relatively well at measuring variability in soil moisture, regardless of, so it's a matter of whether, if you're interested in the relative variability of soil moisture as opposed to the absolute volumetric water content, lots of sensors can perform relatively well if they're calibrated correctly and maintained. If they're not calibrated, then the performance degrades substantially. So it's really more of a calibration issue as opposed to a, although there are sensor-specific differences since given the variety of different types of technology that's used. So it's a very challenging question to answer in a good way, but thanks, Pierre, for asking it. All right. Peter asks about what is the soil moisture index with the KBDI. KBDI uses, if I recall correctly, some kind of DUF moisture. So it's kind of a water balance type calculation that is embedded in it. But I must admit, I don't know the exact answer to that question off the top of my head. Then Sujay asks about the future of the North American Soil Moisture Database. Great question. The funding for the North American Soil Moisture Database is tied to this NSF project that I have that ends in February of 2016. It's as well as being part of this project is something that I feel strongly about the value of, so I will be looking for ways to maintain that. I think there ultimately could be some value in merging this into the National Soil Moisture Network, and so that the historical data and all of these various networks are available as well as in near real time, and satellites and land surface models all in one place. I think we're a couple steps away from making that happen, but we're definitely interested in maintaining the North American Soil Moisture Database, and it won't go dark just because the NSF funding ends. All right, 2 more questions. Providing high spatial resolution soil moisture data. So the National Soil Moisture Network provides the in situ location. So these are at a point. So there is, for each of the dots on the map, there is a physical sensor in the ground at a particular depth. So that's, I guess, as high as the spatial resolution as one can get. When we talk about integrating data from NLDAS or from SMAP, those obviously have different resolutions. There is a group, Jonathan Case has contacted me previously, and he's running the NOAA LSM at 0.03 degrees over the continental United States, and those data I think are available in real time. So that is something that certainly could and should be integrated within this, and that would be that's a very high resolution, spatial resolution model output, and something that he was encouraging us to include within the National Soil Moisture Network. So that's a good point. And last question in terms of freezing soils, most of the in situ sensors cease to function once the soil is frozen. And so that means that most of the, even if they're continuing to report measurements, those measurements can't easily be turned into a meaningful value. And so there are some types of technologies that work around this. And one of the papers that recently came out in Journal of Applied Meteorology and Climatology, we were actually using NLDAS soil temperature data, since not all these sites measure soil temperatures, to quality control the data so that we can identify periods when the soil is frozen. And ultimately, this would be a nice addition to the National Soil Moisture Network as well, is to actually implement this indication of when soils are frozen so that we can notify or flag users that the data may be unreliable at that point. All right, well, thank you for the questions. I'm going to continue on here. I realize that I have very little time remaining, so this will be moving to the rapid fire portion of the talk. So I just want to talk briefly about land-atmosphere interactions and seasonal climate forecasting. This is something that, as I mentioned, was the motivation behind the development of the North American Soil Moisture Database. As a climatologist, it's also something that is near and dear to my research program, is thinking about not only monitoring current conditions, which is what the National Soil Moisture Network gives us the capacity to do, as well as a lot of the other excellent efforts that were mentioned in the questions, but how can we use observations of soil moisture, regardless of where they come from, to help give us a sense for what's going to happen in the future. And so the work that I've been doing over the last 5 years was focused on specifically understanding how soil moisture influences the climate system on seasonal to interannual timescales, focused on the U.S. Great Plains. And we've published a number of papers looking at both soil moisture temperature coupling and soil moisture precipitation coupling. Today, I'm just going to focus on the soil moisture temperature coupling because it's cleaner and easier, and there's probably, at least for some of the regions that we've looked at, more predictability in that regard. So when what kind of motivated this, for me being in College Station, Texas, there is a strong correspondence between precipitation and temperature within the state. So this is a figure put together by the state climatologist, John Nielsen Gammon, that shows for the entire state of Texas, each dot represents the June, July, August rainfall for the state of Texas versus the June, July, August temperatures. And we see 2011, which was a record drought event for the state of Texas, being a significant outlier. But overall, all of these points do tend to show this inverse kind of relationship, that as precipitation increases, mean summertime temperatures in Texas tend to decrease. And so there's some land atmosphere reasons for why that's the case, as well as some other reasons for why that's the case. Many of the drought episodes that have occurred in Texas are associated with sea surface temperatures. And so the 2011 event was certainly related to the La Nina conditions that existed. And there was this prolonged period prior to the summer of 2011 that started in October 2010 of really dry conditions over much of the southern United States, and especially the state of Texas. When we look in this Hurling paper, they did the simulations where they compared what happens in their model when you have dry conditions during that fall to spring period prior to the summer, and what influence that has on the model. And so in the left-hand graph, there's a clear separation here between this green line, ones where we have relatively wet October to May's versus the antecedent, when the antecedent conditions prior to the summer are relatively dry. We see that there's a clear separation. This is, again, the 2011 observed value superimposed on there. So we see that even though it's toward the extremes based on what this model simulation shows, it's much more in line with conditions when we account for those antecedent conditions. And so for this comes down to partitioning of energy and this idea that latent and sensible heat are influenced by the availability of soil moisture, and so that when soil moisture is between the wilting point and the critical value, we see that there's a strong linear relationship between the evaporative fraction, the ratio of latent heat to total net radiation, and when it's outside of that, we either have relatively dry conditions where it's all sensible heat and there's no relationship, or if the soil is relatively wet, if it's above this critical value, then we're no longer in a moisture-limited regime, we're in an energy-limited regime. And so what controls the evaporative fraction and the amount of latent heat at this part of the graph is how much radiation is available. And so we're particularly interested when we think about land-atmosphere interactions and what's going on in this blue box. We evaluated the ability of land surface models to actually capture what's going on in the observations in this paper in 2014, where we looked at the soil moisture evaporative fraction relationships that exist at various ARM sites within atmospheric radiation monitoring sites within the Great Plains. So this is a site from Ashton, Kansas, and it shows daily evaporative fraction versus soil moisture during the growing season of 2006. And then we compared the observed relationships to model-derived relationships, and then also showed how these how these relationships vary over time. So the idea that even though this overall concept of the fact that we see stronger relationships between soil moisture and evaporative fraction in the moisture-limited regime, and that's everything to the left of these lines here. There are certainly seasons or years and locations where that's not the case, and there are also years and locations where we actually see relatively strong linear relationships above what that critical value is. So this led us to want to use the soil moisture database, the observed data, to look at land-atmosphere interactions. And so I'm going to skip through my advertisement here for the North American Soil Moisture Database. If you want to go explore it, soilmoisture.tamu.edu. But we focused specifically on conditions within the state of Oklahoma. The reason is that this is identified as a location with strong land-atmosphere coupling, and it's also a location where there's lots of soil moisture data for us to use. And in this paper that came out last year, we looked at the relationship between in situ soil moisture and extreme temperatures. And so basically, can we use in situ soil moisture to predict a month ahead or a season ahead what the percentage of hot days are going to be? And so this graph shows the relationship between soil moisture anomalies, so departures from normal based on these 56 sites, and this is done by aggregating data for the entire state of Oklahoma, and then comparing it to the percentage of hot days. So these are the number of days in a month that exceed the 90th percentile for maximum temperature. And each of these lines here is the fit of a quantile regression model between the soil moisture anomalies and a specific quantile of the data. And so we see that the slope of these lines increases substantially, and that there's the strongest relationship for the 95th quantile of the data. We did this for seasons, This shows how the slope of those varies over time. And then we employed the models that we developed in a very simple seasonal forecasting approach. And so in this case, we used each of those quantile regressions and conditioned them based on what the soil moisture was in a particular month, and then used the soil moisture data from a particular month to forecast what conditions were in the next month. And the prediction, we used a weighted scheme like the Climate Prediction Center does, where we attempted to determine what the likelihood was of below normal, near normal, or above normal conditions specifically related to the percentage of hot days. And the results of that are reported in this table, which show that we have the height key skill scores down in this line, and then our model sensitivity and specificity. And so those two parameters allow us to assess how well the model is doing in terms of accurately identifying so for sensitivity, it's the ability of the model to identify a condition correctly. And for specificity, it assesses the ability of the model to exclude a condition correctly. And so if we look at the 0.86 number, for example, in this below normal category, that says that the certainty that the percentage of hot days will not be below normal is 86%. And if we go over to this, it says that the certainty of that the percentage of hot days will not be above normal is 79%. So in terms of specificity, the model performs relatively well. In terms of skill score, this simple model does okay, but not, and kind of interestingly to me at least, that the skill is greatest in spring and lowest in summer when we look at it on a seasonal basis. And so in order to compare sort of these skill scores versus alternative methods, if we look at the NOAA Climate Prediction Center's monthly mean temperature forecast at a 2-week lead, their height key skill scores vary between 10 and 20. So that is of a similar magnitude to what our forecast skill for percentage hot days was. So this is just sort of an initial demonstration of what the potential is for using soil moisture data for month ahead or season ahead temperature forecasts. And we've also looked at this in terms of precipitation as well. But obviously there's not time to cover any of that. Another way that we can look at things is spatially. And so why choose Oklahoma? Well, this particular map gives us a little bit of indication. So here we're using the 1-month SPI, so this would, and the monthly maximum temperature in the next month. So this, here we represent the 1-month SPI as a proxy for soil moisture, and this is based on PRISM gridded data over the United States. And then we correlate it with temperature in the next month and report those. So the darker oranges here are regions where there's relatively strong correlation between, let's say, SPI in July and August temperatures. And this is for the period from 1992 to 2011. So this is just one time period that we analyzed. And if we look at other time periods, so this is 1931 to 1950, we see that the relationship, the coupling, if we want to represent this in that kind of framework, between the land surface and the atmosphere changes over space and over time, and that's a significant question of interest that we're kind of looking at. So I think I'm going to stop there because I've utilized all my time, and I will happily stay on the line and take questions, but I'll also happily release people to their own devices.
So I think we can keep going with some questions for a few minutes if people will just type their questions into the chat box. And if you have to go, since it's now 4 o'clock, feel free. But also, Stephen, I just want to say thank you for this presentation. This was really interesting and a very exciting work that you're doing.
Yeah, thanks again for the invitation. All right, so the question in terms of what averaging period for SPI was used for these temperature correlations. So here, the 1 month SPI is based on the entire period of record for the PRISM data. So this is 1895 through 2011, I think, or maybe we went a little bit further into 2013, but it's the PRISM period of record. Good question. Did we try the 3-month or 6-month SPI? In this case, I don't have those plots here. The reason that we chose to focus on the 1 month SPI was because prior work, and so some of the European studies that have come out looking at soil moisture and extreme temperatures and some of the other previous literature had used the 1 month SPI as their proxy for soil moisture. And so that was our initial attempt, but we do also have the results for the 3-month and 6-month SPI. I'd like to be able to describe exactly the way those look, but it's been a few months, so if you're interested, I can definitely send those to you, or Trent Ford, who's an assistant professor now at Southern Illinois, who was my PhD student who did a lot of this work. He also is a good person to ask about that.
I want to say last call for any questions. Okay, well, I don't see any other questions coming to the chat box. So I want to say thank you again to Stephen, and I hope that everyone can join us next week, next Friday at 3 o'clock Eastern, with Bridget Scanlon presenting, and everyone have a good weekend. Bye-bye.
Thanks very much.